This is a Math 3 summary video for the lesson titled Building Strong Roots. This is a Solidify Understanding task. In this lesson, students learn about the fundamental theorem of algebra and explore the relationship between x-intercepts, roots, and factors. When working with quadratic functions, we learned the fundamental theorem of algebra. The nth degree polynomial function has n roots. In this task, we'll be exploring this idea further with other polynomial functions. Quadratic functions and the fundamental theorem of algebra. The fundamental theorem of algebra states that the degree of the polynomial matches the number of roots that the polynomial has. So since quadratic functions have a degree equal to 2, they should have 2 roots. So a root, remember, is the value of x when f of x equals 0. So that's how we find the roots. So algebraically, to find the roots, we'll set f of x equal to 0, and then we can solve. So to solve this quadratic function, I'm going to factor. My factors are numbers that multiply to get -6 and add to get +1. So that would be +3 and -2. Now that I have this in factored form, I can use the zero product property. And since I'm multiplying two values to get an answer of 0, one or both of these values have to equal 0. So I'm going to set each one of my factors equal to 0 and then solve, and then here are my roots. My roots are 2 and -3. I can also tell from the graph f of x equals 0 when x equals 2 and x equals -3. So I have 2 real roots. So for b, g of x equals x squared minus 2x minus 7. I set this equation equal to 0 because it's hard to tell from this graph exactly where the x-intercepts are. So I know that this is not going to factor because there's nothing that multiplies to get -7 and adds to get -2. Since it doesn't factor, I can either complete the square or use the quadratic formula to solve this equation. And I'm going to complete the square. So to complete the square, I'm going to take half of b. Now b is -2. I'm going to take half of b and square it. So half of -2 squared is +1. So I'm going to add +1, but I'm also going to subtract +1 because I don't want to change the balance of the equation. My next step then would be to factor this part and get x minus 1 squared, and then I combine -7 minus 1 to get a -8. Then I'll add 8 to both sides, and then take the square root of both sides of my equation. My next step is to add 1 to both sides of the equation, and I get 1 plus or minus the square root of 8. And I can simplify that to 1 plus or minus 2 square roots of 2. So that's 1 plus 2 square roots of 2 and 1 minus 2 square roots of 2. So those are 2 real roots. They're irrational because of this square root of 2, but they are real. For c, when I set this equation equal to 0, factor, and then I set each factor equal to 0 and solve and get x equals 2. And I had it twice. That's because there's only one x-intercept right here at x equals 2. So because I had this twice, I have one real root, but it has a multiplicity of 2 because it happened twice. For d, I can see that there's no x-intercept, so I know that my roots are not real. So to find my roots, I can either use the quadratic formula or completing the square. This time, I'm going to use the quadratic formula. So I've identified a, b, and c from this standard form of my equation, and I have the quadratic formula. So I just substitute the values in the correct location, simplify what's underneath my square root. The square root of -4 is 2i. And then I divide 2 into 4 and I get 2, and I divide 2 into 2i and I get I. So my roots are 2 plus I and 2 minus I. So I have 2 non-real roots. So roots are values that make f of x equals 0. So roots are written as x equals a. X-intercepts are points where the graph of the function crosses the x-axis. X-intercepts are written as a coordinate, a0. If x equals a is a root of f of x, then x minus a is a factor of f of x. Let's take a look at this cubic function here. Its x-intercepts I can locate from the graph. I have one here, here, and here. So that is negative 2, 0, 0, 0, and 5, 0. So my roots are x equals negative 2, x equals 0, and x equals 5. So my factored form for g of x equals x minus a negative 2, so x plus 2, and then x minus 0, and x minus 5. So let me clean this up a little. I'm going to just write x, and then x plus 2, and then x minus 5. I want to verify that this is correct, so I'm going to multiply to make sure. So I multiply x into x plus 2. I get x squared plus 2x. Then I'll multiply this times x minus 5. Combine my like terms. I have x cubed minus 3x squared minus 10x. And that is the same thing that g of x started off with. So I know that g of x does equal x times x plus 2 times x minus 5. Here's another example. The x-intercepts. There's one right here at negative 4, 0. And then there's one right here at 1, 0. So my roots are x equals negative 4 and x equals 1. Now this is a cubic function, but I only have 2 roots. And the reason why that's happening is because of this root right here at x equals negative 4. Here you can see that the function is changing direction right at the x-intercept. Because that's happening right here, I know that x equals negative 4 has a multiplicity of 2. So my factored form, I'm going to write x, so it's minus a negative 4, so I'm going to put plus 4. And I'm going to square this since it's happening twice at a multiplicity of 2. And then I have x minus 1. So f of x equals the quantity x plus 4 squared times the quantity x minus 1. So is this consistent with the fundamental theorem of algebra? Yes, because this root has a multiplicity of 2. So we have a total of 3 roots. One just has to be counted twice. Here's one more cubic polynomial function, and we need to find the roots of p of x. Now we know that this is a cubic function. It tells us in the direction, but we can also see that when we look at these two factors, this one has a degree of 1 and this one has a degree of 2, so total that would end up being a degree of 3. So we have a cubic polynomial function. So that means we're going to have 3 roots. We can identify one of them right here at x equals negative 3. We can also identify it from the factored form, because that's x minus negative 3, to get that negative 3. The other 2 roots are a little trickier to find. So let's make p of x equal to 0, so that way we can solve our equation and find the other 2 roots. So since this is in factored form, and it's set equal to 0, we can use that 0 product property and set each of our factors equal to 0. Over here, when we solve, that's where we get our negative 3. Here, when I'm solving, I'll subtract 4 on both sides of my equation. X squared equals negative 4. When I take the square root of both sides of my equation, I'll get x equals a positive or negative 2i. So my other 2 roots, I have x equals a positive 2i and x equals a negative 2i. All right, so in summary, the fundamental theorem of algebra tells us that the degree has to match the number of roots. It is possible to have 2 non-real roots. So here we had 2 imaginary roots. But you can have 2 non-real roots. They do always come in pairs. Or you can have a root with a multiplicity of 2. But in total, for a cubic function, you'll have 3 roots. For a quadratic function, you have 2 roots. For a linear function, you have 1 root. And for a quartic function, a polynomial with a degree of 4, you'd have 4 roots. Alright, that's it for this video. Thank you for watching.